All right, I think this video will be able to knock out these last two learning objectives, which are kind of summary of what we have been talking about here, starting with atoms, moving up through molecules, water, carbon chemistry, and then into large biological molecules. And again, these are all things that are universal to all living things as we know here on Earth. So can you identify these different structures if they're not labeled? So let's see. What do we got going on here? Well, you've got these two molecules that are similar in their appearance. They have different functional groups on them. But remember, in these types of illustrations, what we're looking at is everywhere you see a corner, there is a carbon atom. And any bonds that aren't drawn in for a carbon that, you just remember every carbon atom is going to have 4 bonds on it. So basically what you're looking at is a bunch of carbon and hydrogen. And it's arranged into these 4 rings, and those 4 rings should tell you something about these molecules. So the fact that it's mostly hydrocarbon should let you know that what we're looking at is which one of our 4 classes of large biological molecules? Lipids. And the fact that they are in these 4 ring structures like this should tell you that these are steroids. This is testosterone here on the right, which I can tell because it's got this ketone group on it. It's testosterone. This is estradiol. It's got a hydroxyl group, which is an alcohol. So estradiol. Okay, so let's do this one that's a little bit simpler. It's got all of the carbons and hydrogens drawn in there. We've looked for the functional groups. Should recognize that one in red there, that's a carbonyl group. And so you've got a carbonyl group and you've got a lot of hydroxyl groups. And that's about it. So carbon, hydrogen, and oxygen. Maybe if we were pressed for time, we wouldn't have time to count up all the carbons, hydrogens, and oxygens. But let's at least count the carbons. There's 1, 2, 3, 4, 5, 6. Okay, so I'm gonna take a wild guess here and say that there's 12 hydrogens and there's 6 oxygens. Let's count the oxygens. Why not? 1, 2, 3, 4, 5, 6. So CH2O times 6 means that what we're looking at here is a simple carbohydrate. And in this case, we're looking at fructose, although I don't expect you to know that. Just recognize that with that carbonyl group and the oxygen and the hydrogen, that being it, it's a carbohydrate. Okay, we just saw this not too long ago. What's going on here? Hopefully you recognize there's an amine group, there's a carboxyl group. So organic acid, amine acid, amino acid. Yep, with the different R groups on here. Different types of R groups. Don't need to know that this is whatever it is. Methionine, I think. Anyway, see, I don't know, so you definitely don't need to know. And what's happening to them? They are being put together. We're forming a peptide bond. Amino acids being put together by peptide bonds. And what is this process called here? That's dehydration synthesis. So if we wanted to take this amino acid back off because we ate it and we don't want to form a chicken, we don't want a chicken protein, we want a human protein, we could break that peptide bond through hydrolysis. Okay, so we've got a squiggle with some extra lines in there. And then over here, we've got a functional group that you should recognize. There's a C double bonded to an O and also to an OH. This is another organic acid. What are we looking at here? It is an organic acid with a bunch of hydrocarbon on it, just carbon and hydrogen. A few double bonds. Ooh, double bonds. That should tell us something too. So hopefully you recognize that this is an unsaturated fatty acid. Why is it unsaturated? Because it has double bonds. If it has double bonds, that means we have the potential to put more hydrogen onto this molecule by breaking those double bonds and forcing those carbon atoms to accept more hydrogen. Wouldn't be the healthiest choice for us to go and hydrogenate our unsaturated fatty acid, but you could do it. All right, and I just have one more slide to show you here, asking about the monomers and polymers in carbohydrates, proteins, and nucleic acids. Remember, lipids do not form true polymers because the most complex lipids that you're going to get in the form of fats only have 3 fatty acids. It's not like you're going to have a monstrously long 1,000 million billion chain of the units of carbohydrates, proteins, and nucleic acids. So what might be handy to do is to draw out a table like this: carbohydrates, lipids, proteins, nucleic acids. Here you can see they've indicated monomers or components, polymer or larger molecule, and then the types of linkage. We talk a little bit about that. So for carbohydrates, monosaccharides can be linked to form polysaccharides by glycosidic linkages. For lipids, we can attach fatty acids to glycerol. We can form triglycerides. I don't think I talked about ester linkages, but it's another form of dehydration synthesis. Proteins are made up of amino acids that are made into polypeptides. The polypeptides may be joined to form a functioning protein by peptide bonds. And then nucleic acids are made up of nucleotides. The polynucleotides are our DNA and our RNA molecules. And the bonds between those, I don't think I emphasized this, but those are phosphodiester linkages. So for the ones that polymerize, carbohydrates, proteins, and nucleic acids, you definitely want to know these first 2 columns. And I did mention a couple of these types of linkages. So we'll say that they're not as important as what's in the first 3 columns here. We'll include this column here. And that is it. That is one big, monstrously long chapter. And from here on out, they'll be a lot shorter. But still a lot of amazing stuff to learn. But this will be it for our first exam.